We're going to explain to you how you're going to do your statistical analysis for your molar mass of your monoprotic acid in experiment 19. You'll be working in groups of 4 or 5, and you're going to wind up having anywhere between 6 and 10 different possible values for the molar mass of your specific unknown monoprotic acid. We'll do an example where we actually have 6 different values for the molar mass of the monoprotic acid. You'll be collecting those on the discussion board for the experiment 19. And then after you've collected everybody's results, this might be the results of 3 different people because each person is going to be presenting 2 different molar masses that they will theoretically have calculated during the experiment. When we take a look at each of these numbers, all of the molar masses seem to be about 86 to 87 grams per mole, except for trial number 4. That one's 81.18. Now, why is that so bad? Well, there could be a reason for why this one is so far away from the other measurements, which means that it's not precise. Precision has to do with how close measurements that are repeated are to each other. It could be that there was a gross error that occurred. So if an identifiable gross error caused this imprecision, we would immediately throw out that data point and not use it to calculate the average molar mass from all of our different trials. This would be something like maybe you got to the pink endpoint in the titration, then added 2 extra drops by mistake. That's an identifiable gross error, certainly going to give you an imprecise value for your molar mass. It could also be maybe there was a bubble in the stopcock tip and the bubble blooped out in the middle of the experiment. That's going to give you an error. Or some of the solution spilled, or some of the solid acid you were weighing out didn't all dissolve and got stuck up on the side of the flask. Any one of those would be an identifiable error, and you would be able to ignore the point. However, if there's no identifiable error that caused this imprecision for trial 4, then the only way you can ignore that is by using a statistical test, and we're going to show you today how you do a statistical test called a Q-test. The first thing you want to do is you want to list all of the different values for your molar mass in either ascending or descending order, just so they go in order. So I'm going to actually arrange these from lowest to highest. You could have done highest to lowest, but either way would be fine. And we actually only want to ever look at the highest and lowest values. So we're going to look at the 88.22 and the 81.18. Those would be the only ones that could be suspect of being not precise. In this case, the 88.22 is so close to the 88.16, I would not necessarily guess that was an imprecise value. But clearly up here, the 81.18 is almost 5 whole grams per mole away from the trial 3 value. So there could have been a gross error that occurred we just were not aware of. And so if we arrange them in this particular order, we're going to try to calculate something called a Q value. To get a Q value, what you do is you figure out what the difference is between the suspect value, which is the 81.18, and the next closest measurement to it. And that's why we list these in order. So the next closest measurement is 86.10. The difference between these two is called the gap. We then calculate the difference between the lowest and highest molar masses in the entire experiment. That would be between trials 4 and 6. That's called the range. And if you take the gap and divide it by the range, that's going to give you a statistical value that's called Q. So Q will be whatever the gap is divided by whatever the range is, and this always comes out to be a number between 0 and 1. It's essentially a decimal fraction. So if we calculate our gap value by going 86.10 minus 88.18, and calculate our range by going 88.22 minus 81.18, and you always subtract those to make them positive numbers, we calculate a Q value of 0.70. So statisticians have figured out what Q would have to be in order to assume statistically that that 81.18 grams per mole probably should not be included in our average calculation for our molar mass because probably a gross error occurred. And in your lab, you have a table of what are called Q95 values. And the Q95 depends upon how many different experiments you did, how many trials you did. In our case, we've done 6 trials. So if you locate on the table 6 trials and see what the Q95 number is, if Q is bigger in this case than 0.625, that means that statistically the 81.18 is probably so off because there was a gross error that occurred, and therefore statistically we can ignore it and not use it to calculate the molar mass of this monoprotic acid. So because our Q value that we've calculated is greater than the Q95, that technically means that the data point can be ignored with a 95% confidence level that we're throwing it out because it was probably made by a gross error. There's actually a 5% chance that there was no gross error and we should include it. But we usually statistically like to look at a 95% confidence level. So in this case, we would be able to throw out the 81.18 grams per mole. So when you have your 6 to 10 different values in your lab today, what you're going to do is you're going to test the highest and lowest ones to see if their Q value comes out greater than their Q95. If they do, you can throw the value out. If it doesn't, you have to keep the value. In this case, we can throw out trial 4, so I'm not going to include it in my calculations for the mean, and then the standard deviation, and then the relative standard deviation, because those are the 3 numerical values we want to get from this experiment. So to calculate the mean, which would be the average molar mass of the monoprotic acid, you're going to take all of the trials now that are not being excluded, so that's 5 trials in my case, and to calculate an average, you just add the 5 different values together and divide by how many trials there were. So our mean is going to be the sum of each one of these different values here divided by 5, and because they're all accurate 2 places past the decimal point, when I get my mean value, it's going to be written 2 places past the decimal point. And so I calculate a mean value of 87.30 grams per mole. And so in your data table, you would enter the molar mass of the monoprotic acid, the mean molar mass of the monoprotic acid, as 87.30. That's one statistical calculation you're going to want to do. The next one you're going to want to do is something called standard deviation, which is a statistical measure as to how spread out your values are for the different trials. It's really telling you how precise the work is you're doing. If we did hundreds and hundreds of different trials on trying to calculate the molar mass of this monoprotic acid, and we measured them all, different molar masses along the x-axis, and the y-axis is how many values we get for each one of those molar masses, we're going to probably get a bell-shaped curve like this, which are going to all center around the average or accepted molar mass of the monoprotic acid, which is 87.30 grams per mole. Now, if you do really, really good work, then this particular bell-shaped curve is not going to be spread out so wide. It's going to be really narrow. That would be very precise work. The more spread out it is, the more variation there is in each person's trials when they do this, and we would say the work is less precise. So one way to show how spread out this curve is to calculate something called a standard deviation. And the standard deviation, if we graph standard deviations on the x-axis, a standard deviation unit is how much the value you calculate in your lab can deviate from the average on either a positive or negative direction. So however big this value here is, which is called 1 standard deviation unit, that tells you a measure of the spread of the data. If this is a really small number, that means this whole curve is very narrow. You're doing very precise work. If it's a really big number, that means that the data is spread out and your work is not so precise. It turns out statistically that when you calculate what the standard deviation is, and you calculate what the value is for this point in the graph and this point in the graph, then statistically, 68.2% of every trial you ever do to calculate the molar mass of this particular acid will lie within the range of the standard deviation plus or minus away from the molar mass. If you go 2 standard deviation units away from that, and that would be out to here and to here, that covers a huge amount of the curve. That actually covers over 95%. So if you're within 2 standard deviations, then we would imagine that you're going to wind up always fitting in that range 95% of the time. People tend to express the spread of this curve in terms of 1 standard deviation unit. So whenever you see a standard deviation unit, you will know that 68.2% of the time, we would expect a measured value to fit within that range around the particular mean. Now, how do you calculate a standard deviation? What you have to do is you need to know the average molar mass value, which is 87.30, and then you calculate a deviation for each of the trials in the experiment. So for the first trial, for example, the 86.10 grams per mole, which is from trial 3, if we subtract 86.10 from 87.30, I'm going to get my deviation. That's how far off that particular trial is from the average. If I square that, I'm going to get a squared term for the deviation. This is the deviation squared. And what we're going to do is we calculate a deviation squared for every single trial. So I have 5 trials. I'm going to do this 5 times. So notice what I've done. I've just subtracted the mean with the particular trial's value. Once I subtract those, I square it. And then I add all those together. Then I'm going to take the number of trials I'm using here, which are 5 trials. Remember, I threw out trial 4, so I'm not using 6, I'm using 5. I'm going to divide this by 1 less than the number of trials I'm using. So the number of trials minus 1 goes in the denominator. Then, if you take the square root of this entire operation, you will have the standard deviation. It turns out that this value we get, statisticians have shown, will give you a value that if you're plus or minus that value from the average, 68.2% of the time, you're going to have a measured value in that range. So if you do this, this comes out 0.991, or rounding it to 2 places past the decimal point, because every one of my measurements is 2 places past the decimal point, I get 0.99 grams per mole. So this will be the reported standard deviation for this particular experiment. So when we imagine this experiment being done by a titration to determine the molar mass of a monoprotic acid, we would imagine that 68.2% of the time, people would essentially be between 86.31 grams per mole all the way up to 88.29 grams per mole, because the standard deviation is 0.99. Now, the calculation is a bit intensive. You can certainly do this even if you have up to 10 trials. It's not the end of the world. But if you want to have it done for you, you can go to www.mathportal.org. If you go to that website, at the bottom left, it says top 5 calculators. And one of those top 5 calculators is a standard deviation calculator. Select that. When you select that, there'll be a box for you to enter data in. I've got 5 pieces of data to enter, so I would enter 86.10, comma, 86.48, comma, 87.54, comma, et cetera, et cetera. So all the data points, in this case 5, are entered separated by commas. Right below, there's a little button that says Show Me an Explanation. Click on that, and then click Calculate. When you do that, you will see the standard deviation given, and it'll calculate the mean for you, so you'll actually have both of those things calculated at this website. The sigma sign on there is what is the standard deviation. So in this case, it would have said sigma equals 0.99, and there's a capital X with a bar over it, which is the symbol for mean. That's going to say 87.30. So both of these would be given on that website if you want to use it for your calculation. The last thing we're going to calculate is something called the relative standard deviation. And it's just presenting the standard deviation in a percentage of the average molar mass. So how do you get the percentage of the average molar mass? Well, you take the standard deviation, divide it by the mean value, and multiply it by 100. This comes out 1.135. Actually, that 5 was a 4.7 and got rounded up to a 5. So this technically rounds to 1.13%. So what this means is your standard deviation is 1.13% of the molar mass, and that's just another way to give you a way to represent standard deviation. Oh, I'm going to calculate the molar mass as 87.30, and every time somebody does this in lab, we would imagine that 68.2% of the time, they're going to be within 1.13% of that. So these will be the statistical values that you're going to calculate for your experiment 19.